Today we discuss chapter 3, the tangent space. First we have a definition of tangent vectors. Let f from u to r be a smooth function. Let c be a real number such that f inverse c is non-empty. So that is a non-empty level set and p belongs to that non-empty level set. A vector at P is said to be tangent to the level set f inverse C if it is a velocity vector of a parameterized curve in R plus 1 whose image is fully contained in f inverse C. So this is the definition of a tangent vector. So tangent vector is the vector at the point P which is in the level set such that that vector should be a velocity vector of some parameterized curve which is fully contained in that surface or that level set, not surface, that level set. Suppose this is our surface. Surface means level set f inverse C. Then in order to get a tangent vector at the point P of this level set, we need to consider a parameterized curve which fully contained in this level set f inverse C, and the parameterized for this parameterized curve, this is a velocity vector. Okay, so this vector is called tangent vector. Okay, so a velocity vector of a parameterized curve at P is called tangent vector. The only thing you need to remember is that parameterized curve should be contained in this f inverse C. Now we have a lemma. The statement of the lemma is the gradient of f at P belongs to f inverse C is orthogonal to all vectors tangent to f inverse C at P. So gradient of f is denoted by this del f, and del f at a point P is defined as the vector P comma dou f by dou x1 etc dou f by dou xn plus 1. This is the gradient of f at a point P. That means gradient f assigns a vector at P. Okay, the vector component of that del f is dou f by dou x1 plus dou f by dou x1 comma dou f by dou xn plus 1. Okay, so we need to prove that gradient of f at P is orthogonal to all tangent vectors. So we choose a tangent vector V. We can say that this V is perpendicular to del f of P. Okay, so this is the tangent vector at P. Then this holds. This is we have to prove. For this, we need to remember chain rule for multivariate functions d by dt of f of x1 of t etc xn plus 1 of t equal to this. This x1 of t is each xi is a function from some open interval or closed interval a b to this r. Okay, so this defines a real number x1 of t. Similarly, xn plus 1 of t is a real number. So this constitute an element in Rn plus 1 or subset of Rn plus 1. So d by dt of f of this is defined as, and obviously this f is a function from u, which is the subset of Rn plus 1 to R. This is the behavior of f. So the derivative of the composition is defined as dou f by dou x1 into dx1 by dt. Since this x1 is a function, is a real value function defined on a closed interval ab, so you can write the derivative of x1 as dx1 by dt. So plus etc dou f by dou x n plus 1 into dxn plus 1 by dt. So this can be written as this is same as uh, dou f by, we write it as dot product of two vectors at the point P. We have dou f by dou x1 comma etc dou f by dou xn plus 1 dot P comma dx1 by dt etc dxn plus 1 by dt. So actually this is the this can be written as dot product of these two. by the definition of the dot product, then you can write this is equal to del f of alpha of t dot alpha dot t. Okay, so this alpha of t is x1 of t plus x comma etc xn plus 1 of t, and alpha dot is in fact this alpha dot is a vector at alpha of t. Okay? At the point alpha of t, this assigns this vector dx1 by dt etc dxn plus 1 by dt. In fact, this is the alpha velocity vector of alpha, and alpha dot this represents the vector part of the alpha. So you should careful about this. You need not write like this. You need to write p comma this dx1 by dt etc. Now we can prove the statement. We start with the tangent vector. V is the tangent vector to f inverse c at P. Then you can find the definition of the tangent vector gives a parameterized curve alpha from I to Rn plus 1 with V is equal to alpha dot t naught. This V is the velocity vector of alpha at t naught, and alpha of t naught is the point P. And the image of alpha fully contained in f inverse c. This is the definition of tangent vector. From this image of alpha contained in f inverse c means if you consider any alpha of t, then f of alpha of t is z. Okay, that is the condition. F of alpha of t equal to c. By differentiating, we can get the right side is 0. So 0 is equal to d by dt of this f of alpha of t. D by dt of f composition alpha of t naught, that means derivative of f composition alpha at the point t is equal to t naught. That is equal to del f of alpha of t naught dot alpha dot t naught. This is what we have discussed in the reference. So that is equal to del f of p, since this alpha of t naught is p and alpha dot t naught. Alpha dot t naught is the vector at p or alpha of t naught. From this you can say that this dot product is 0, hence these are orthogonal. Obviously this v is equal to alpha dot t naught which is orthogonal to del f of p. This is the remark on that lemma. If del f p not equal to 0, the set of all tangent vectors to f inverse c at point p, okay, is contained in the n-dimensional vector space del f of p per of rpn plus 1, consisting of all vectors orthogonal to del f p. So this del f p perpendicular, this is a vector in r p n plus 1. Okay, so this is the vectors orthogonal to this del f p. If we choose any non-zero vector, then the set of all vectors orthogonal to del f p is defined as del f p perpendicular. Okay, this is always a of dimension 1 less than this dimension of this vector space. So that is nothing but dimension n. Okay, so we can say that any tangent vector belongs to an n-dimensional vector space which is which are perpendicular to del f p. And this point, a point p belongs to Rn plus 1 such that del f p not equal to 0 is called a regular point. This is the definition. Now we have a theorem. This characterizes the tangent space. The statement is, if U be a open set in Rn plus 1 and f from U to R be a smooth function, let P belongs to U be a regular point of f. Regular point means del f p at that point is non-zero, and let C is equal to f of p. Then the set of all vectors tangent to f inverse C at P is equal to del f p perpendicular. Okay, so we have some references for this for the proof of this theorem. We know that what is del f p perpendicular? Del f p perp is equal to set of all v belongs to the vectors at P, that is v is equal to p comma v, with the del f of p dot v is equal to 0. Okay, this is the perpendicular vectors of del f of p. Now we have shown that if T is the tangent space, set of all tangents, if we choose a tangent vector v, then that belongs to del f perpendicular. We have shown that v dot del f p is equal to 0 in the previous lemma. So we have t tangent space is always contained in del fp perpendicular. Now in order to prove this theorem, we need to, what is the meaning of this theorem? This theorem says that t is equal to del f of p perp. This is what we have stated in this theorem. The set of all tangent vectors at to f inverse c at p is equal to this. So we need to prove this equality. So in the lemma we have one inclusion, t is contained in del f p perpendicular. Now we have to show that the other inclusion, del f of p perpendicular, contained in t. That means if we choose a perpendicular vector to this del of p, then we need to show that that is a tangent vector. In order to show that that is a tangent vector, we need to get a parameterized curve, and this vector v, which is perpendicular to del of p, is a velocity vector of that parameterized curve. So our intention is to find out a parameterized curve properly. Now we can prove. We start with a vector v which is perpendicular to del fp. That means del fp dot p is equal to 0. Now we define a constant vector field x of q is equal to q comma v for all q belongs to Rn plus 1. Okay, so this defines if this is Rn plus 1, if you first you choose a vector v, then if this is v which is perpendicular to del f of p, then we consider a vector field with this constant vector. Okay, so we are saying v at every point of Rn plus p. Okay, so if we choose v like this, then we consider a vector field at every point, vector field which assigns v at every point. Okay, this will be the constant vector field. Every point we assign this vector. This is what we called constant vector field. So this is x of q is a constant vector field. If q varies, then v remains unchanged. Using this, define a new vector field. Using the vector field x of q, define a new vector field y of q in such a way that x of q minus this times, this is a scalar because the numerator is dot product of two vectors, and denominator is a square of no. So this is a scalar del f into this times del f of q. Okay, then the domain of y. What is domain of y? If we choose any q belongs to Rn plus 1 with del f q not equal to 0, this is defined. Yeah. So one thing you should remember is that if you choose a q from Rn plus 1, and this del f q should be non-zero, then only you can define this. Okay, clearly this p belongs to u, because we know that p is a this point, a regular point, hence del f at p is always non-zero. So p belongs to this u. So this u is a domain of this vector field y contains the point p. Now we have y of q dot del f q equal to 0. Why this is so? We can take del y of q dot del f q. That means we need to take the dot product here, dot del f q. Then del f q dot del f q will give del f q square. You can cancel this del f q square. Then this term will be x of q dot del f q, and we need to take the dot product with this one. So this will be x of q dot del f q minus the same term. So that will give the 0. Okay, and y of p equal to x of p. Okay, if you evaluate y of p here, we can say that this is x of p dot del f of p divided by all the q's are changed as p. So this x of p dot del f of p. What is x of p here? That means if we evaluate y of p, that is x of p minus observe this bracket. So this is x of p dot del of p divided by norm of square of norm of something into del f of p. But this is our v, and this is del f of p. we have chosen this v in such a way that the dot product is 0. So this will give this term is 0, hence y of p coincides with x of p, but x of p is nothing but v. Okay, so we can say that if you define new vector field y of q, then this y of q has these much properties: y of q dot del of q is 0, and y of p coincides with x of p, that is equal to v. Now corresponding to this y of q, okay, we can get an integral curve. This is by the theorem discussed in chapter 2. Every smooth vector field has a maximal integral curve. Okay. Now let alpha be an integral curve of y through p, with alpha of 0 equal to p and alpha dot t is equal to y of alpha of t. Choose this is nothing but the maximal integral curve of y of q. The existence of such curve is discussed in chapter 2. Now we have alpha dot 0 is equal to y of alpha of 0, that is y of p, that is equal to x of p, which is equal to v. So we can say that alpha dot 0 is v. So now this shows that alpha dot 0 is the velocity vector of a parameterized curve, and that is equal to v. That means v is a tangent vector. Okay, so if you choose a vector v which is perpendicular to del of p, from this you can get v is a tangent vector at p. And we can say that d by dt of f of we need to prove that the parameteristic curve is fully contained in that level set. So in order to prove that, we start with d by dt of f of alpha of t. So this is nothing but this, and del f of alpha of t dot y of alpha of t equal to 0, because since this alpha is the maximal integral curve, this alpha dot t coincides with y of alpha of t. Clear? So this is equal to 0. Why this is 0? Here we have y of q dot del of q is 0 for all q belongs to u. Therefore, this dot product is always 0. If this is 0, we can say that this is the derivative of f composition alpha. So this f composition alpha is a constant. But we know that at the point p, this f of alpha of 0, or at the point p, f of p, we have c, because p belongs to f inverse c. So in that case, we can say that this is the derivative 0, and at the point, at least one point, we have the value c. Therefore, we know that this f composition alpha is always p. Okay, so this shows that the alpha of t belongs to f inverse c. That means this image alpha is fully contained in f inverse c. This shows that alpha is a parameterized curve which fully contained in f inverse c, and this alpha dot 0 is this v. Therefore, v is a tangent vector. Now we have a remark: at each regular point P on a level set f inverse C of a smooth function, there is a well-defined tangent space consisting of all velocity vectors at P of all parameterized curves in f inverse C passing through that corresponding point P. And this tangent space is precisely, or this is computed using this subspace del of P perpendicular. Okay, this is the consequence of this theorem. This completes chapter 3. Now we need to work out the problems of the exercise of chapter 3.